Namaste viewers, I am Punit, a GRE instructor at Millionaire GRE. Through this video series, we are learning everything one needs to know about permutations and combinations for the GRE. This is the third and final part of the series. If you have not watched the first two parts, you are advised to go through it before you continue watching this video. These are some additional practice questions I had left you with in the previous video. We will now solve each of these questions one by one. Now coming to the first question, how many 3-digit positive integers can you form by using only the digits 1 or 5 in any combination? Now we have discussed in the previous video that in arrangement of numbers problem, you follow these 4 steps. The first step is to make the required number of slots. Since we are asked for 3-digit positive integers, we will make 3 slots. And there is multiplication between the slots. 0 cannot be in the first slot. Of course, this number cannot have a 0 because you have to make a digit using only 1 or 5. So this is taken care of. Third condition is check whether repetition of digits is allowed. Since nothing is mentioned in the question, we'll assume repetition is allowed. And also, as common sense, you cannot make a 3-digit number using 1 or 5 ones. We talk about the fourth step. It is proceed from left to right unless some other condition is given. There is no other condition given, so we are going to move from left to right. So we are going to first see how many ways are there to fill up the first slot, then how many ways are there to fill up the second slot, and then how many ways are there to fill up the third slot. In the first slot, any of 1 or 5 can come, so there are 2 ways to fill up the first slot. In the second slot also, any digit 1 or 5 can come, so there are 2 ways. In the last slot also, any of the 2 numbers can come. So total there are 8 3-digit positive integers that we can form only using 1 or 5. We can also list down all the digits. Since it's only 8, we can do that. The first 3-digit number is 111. Then we can have 115, 151, 511, 155, 515, 551, and then 555. If we count, it comes out to be 3 plus 3 plus 2, which is 8. Right. Let's now try the second question. Here each wand is assigned a 5-character ID code. The first 2 characters are letters. So the first 2 characters are letters and the next 3 characters are numbers. So these 3 are numbers. We are asked if no 2 wands share the same ID code, what is the maximum number of unique wands we can have? Now there is multiplication between all these slots. In the first slot, 26 letters can come. There are 26 alphabets in total in the first slot. Any of them can come. Now repetition here is allowed because nothing about repetition has been mentioned in the question. So we'll assume that the repetition is allowed. You can have a code like AA111, right? Because repetition is allowed. So in the second slot also we can have 26 letters. There are 10 digits. So in the third slot we can have any of the 10 digits. In this slot, any of the 10, here 10. 26 times 26 is 676 times 1000 will give you 676,000, and this is the answer.
I'll fight you.
Neville, I'm really sorry about this. Petrificus totalis.
Let's try the third question. How many ways can you arrange 4 people, Harry, Ron, Ginny, Neville, in a line ensuring that Ron and Harry are not placed next to each other? Now we'll first find out the number of arrangements in which Ron and Harry are placed next to each other, or Ron and Harry are together. Ron and Harry are together, so take them as one object. There are two other people. So in total you have three objects. If you take Ron and Harry as one object, you have in total three objects. Three objects can be arranged in 3 factorial ways. Now Ron and Harry can be arranged among themselves in 2 factorial ways. Because there are two objects, Ron and Harry, they can be arranged among themselves in 2 factorial ways. So these are all the arrangements in which Ron and Harry are together. If from the total arrangements we subtract all the arrangements in which Ron and Harry are together, we will get all the arrangements in which Ron and Harry are not together. Right? So how many total arrangements can you have with 4 people? There are 4 people. So 4 factorial ways of arranging them. We've already found out the number of ways in which you can arrange such that Ron and Harry are together, which is 3 factorial times 2 factorial. 4 factorial is 24, 3 factorial is 6, 2 factorial is 2. So this comes down to 12. 24 minus 12, you get the final answer as 12. Let's attempt the 4th question. In how many ways can 2 heads be obtained in 3 tosses of a coin? So you're tossing a coin 3 times and you want exactly 2 heads. So either you can have head, head, tail. This means on the first toss you get a head, on the second you again get a head, on the third toss you get a tail. You can also have head, tail, head. Here on the first toss you have a head, then tail, then head. So you're basically finding out how many words you can form which have 2 H and 1 T's. Okay, treat this like a word arrangement problem or letter arrangement problem. You have to find how many words you can form which have 2 H and 1 T. So there are 3 objects. They can be arranged in 3 factorial ways. H is present twice. Hence we will divide by 2 factorial. 3 factorial is 6. 2 factorial is 2. 6 upon 2 is 3. The answer is 3. Even if we list down all the arrangements, we will get exactly 3. Head, head, tail, head, tail, head. We can have another tail, head, head. These are all the arrangements. The answer is 3. We have to treat this problem as a letter arrangement problem. Now let's try a new question. Here there are 24 faculty members serving as judges. We have to form a panel of 3. Out of 24, we have to select 3. And we are given that 9 members have no experience, 6 members have 1 task experience, and 9 members are veteran. We are asked how many panels of 3 judges can be formed such that none of them have any prior experience. None have any prior experience. So we have to select 3. R is 3. Out of the 9 judges who have no experience, we have to select 3 judges out of 9 judges, which can be done in 9C3 ways. And that's the answer to the first part. Let's look at the B part. Exactly 1 judge has experience with at least 1 previous task. So exactly 1 judge is experienced and the other 2 judges are inexperienced. Now how many total experienced judges are there? There are 15 experienced judges. 6 have 1 task experience, 9 are veteran. So there are 15 experienced judges. So out of 15 we have to select 1, which can be done in 15 C1 ways. And implies multiplication. And then we have to select 2 inexperienced judges. There are 9 in total. Out of 9 we have to select 2, which can be done in 9C2 ways. This is the answer to the second part. Now let's move on to the C part. At least one of the judges is a veteran judge. So one is veteran. Let's take a case in which one is veteran and two are other judges. We can have another case in which two are veteran and one is not veteran, one is other. Or there can be another case in which all the three judges are veteran. So there are three cases here. Either one is veteran and two are non-veterans, or two are veteran, one is non-veteran, or all the three judges are veteran. Let's find out how many ways are there in which one is veteran and two are non-veteran. So there are 9 veteran judges, out of which we have to select one, which can be done in 9C1 ways. 15 are other judges. Out of 15 we have to select 2, which can be done in 15C2 ways. Because there was AND, we will multiply. And then we will add, because OR is there, we will add the second case. 2 veterans out of 9 veterans can be selected in 9C2 ways. AND means multiplication. One other judge out of 15 other judges can be selected in 15C1 ways. Or we have another case in which all the 3 are veteran, which can be selected in 9C3 ways. Now there is another way to solve the C part. If from the total judges or the total panels of 3 we can form, if from the total panels of 3 we can form, we subtract all the panels in which no judge is veteran. We will get all the panels in which at least one judge is veteran. At least one veteran. From the total panels, you subtract all the panels in which nobody is veteran. You get the panels in which at least one is veteran. Now how many total panels we can form? There are 24 members, out of which you have to select 3. So it can be done in 24C3 ways. Minus all the panels in which nobody is veteran. There are 15 members who are not veteran. We can subtract 15C3. This will give you the answer to all the panels in which at least one judge is veteran. These two end up giving the same result. So you can do any of the two methods, but this is recommended because it is less time consuming and it is simpler to solve. Now this is an interesting question. There are 5 books and 4 chests. We are asked in how many ways can we put 5 books into 4 chests such that a chest can have any number of books. So if there are 4 chests, chest 1, chest 2, chest 3, chest 4, chest 1 can have all the 5 books. Chest 1 can also have no books. So we can have a case as 5, 0, 0. We can have a case 0, 5, 0, 0. We can have a case 1, 4, 0, 0. So there are multiple ways in which you can put the books into the chests. Now how do we represent this? If we write 5 here, let's say. Now this means any one out of the 5 books is in chest 1. But the chest 1 can also be empty. It can have more than 1 books. How do we represent it? So doing it using this approach becomes difficult. So we'll do it using a different method. We will change our perspective a bit. We will not think from the perspective of chests. We will think from the perspective of books. There are 5 books: B1, B2, B3, B4, B5. Now book 1 can be put in any one of the 4 chests, and book 2 can also be put in any one of the 4 chests. Book 3 can be put in any one of the 4 chests, and 4 and 4. So the answer is 4 to the power 5, which is 1024. So there are 1024 ways of putting 5 books into 4 chests such that a chest can have any number of books. Now I want you to watch a clip.
And Scott is now ahead 2-0. Moving on to the third question of our matchup. And the next question is, the digits 1, 2, 3, 4, and 5 can be arranged to... Scott.
60.
60 is the correct answer.
Guys, IQ is a thing. I didn't even finish reading that question.
Well, I do not know whether IQ is a thing or not, but I'm certain that the kid knew the concept of factorial very well. This question is pretty simple if you can apply the concept of factorial here. The digits 1, 2, 3, 4, 5 can be arranged to form many 5-digit positive integers with 5 distinct digits. So repetition is not allowed. You have to use any digit only once. In how many such integers is the digit 1 to the left of 2? Okay. Let's find how many total 5-digit positive integers can we form using the 5 digits 1, 2, 3, 4, 5. Now there are 5 different digits or 5 different objects. They can be arranged in 5 factorial ways, right? 5 factorial is 120. There are 120 total 5-digit numbers that you can form using 1, 2, 3, 4, 5. Now if you think about it logically, in half of the arrangements, 1 will be to the left of 2, and in other half of the arrangements, 1 will be to the right of 2, right? It will be symmetrical. In half the arrangements, 1 will be to the left of 2. In other half of the arrangements, 1 will be to the right of 2. So if there are 120 total arrangements, in 60 arrangements, 1 is to the left. In the remaining 60 arrangements, 1 is to the right. So the answer is 60. That was all for this video series, where we discussed everything about permutations and combinations for the GRE. Hope you had a wonderful time. If you have any queries, you can reach out to me in the comments section. I'll get back to you. You can also connect with me for a free one-on-one session, the link to which is given in the description. Thank you and have a nice day.